Our first speaker today is Anna Sakovich, who will be talking about towards a space-time intrinsic flat convergence.
Thank you very much for the introduction, and I would like to thank the organizers for putting together this very interesting conference. So the talks in the morning were amazing. I look forward to all other talks in this conference. So I'm going to talk about defining the notion of space-time intrinsic flat convergence. This is joint work with Christina Sarmani. So part of it has been put on archive this summer, and the rest is still in preparation, but hopefully will be done soon. So first of all, why do we? So in a sense, this is related to a talk by Clemens and Felix and also Michael in the morning. But this is kind of different. So we would like to take spacetimes and convert them to metric spaces, and then for this converted spacetimes, which are metric spaces, we would like to apply the notion of intrinsic flat distance, intrinsic flat convergence that was defined by Sarmani and Wenger about 10 years ago. Of course, once the spacetimes are converted to metric spaces, one can, of course, speak about other notions of distance and convergence, Gromov-Hausdorff convergence, or measured Gromov-Hausdorff convergence, but we are focusing on intrinsic flat convergence here. So first of all, why is one interested in something like this? Well, in general relativity, we often have situations when we want to compare to Lorentzian manifolds, spacetimes, or Riemannian manifolds, which are not close in a smooth sense and maybe not even diffeomorphic. So an example of this situation would be like a black hole merger. So black holes merge, topology of spacetime will change. Another example would be, say, we want to compare some spacetime, like our spacetime, which can be quite irregular, contain black holes, to some model like Minkowski spacetime or Schwarzschild or Robertson-Walker, or something which is nice and symmetric. Actually some experts also told us that this notion could be useful, for example, for studying singularities in cosmological spacetimes, because this usually involves blowing up spacetimes and then studying a limit of a sequence. So this might be also applicable there. I think there was a talk by John Lott some time ago within this program where something like this was done. Well, we have this notion of intrinsic flat convergence. So intrinsic flat convergence. So I will be defining it by F. This is the notion of Sarmani-Wenger from 2011. So I'm not going to define it actually, because for most of my talk it won't be very relevant what it actually is. You will be able to understand it anyway, and I think it will appear in some later talks in this conference. For example, in a talk by Raquel Perales. But I will give you some applications of this. Just to show that it is useful and has been used in general relativity. So it has been applied. So I will give you two examples of two conjectures which have been very successfully studied using this notion. And I also will use this opportunity to highlight the work of some of the participants who are in presence here. So first of all, we have stability of positive mass theorem conjecture. So it's a conjecture, but has been proven in many cases already. So conjecture says that so we have a sequence of manifolds Mi, Gi. Dimension here greater or equal to 3. For some proofs we will require 3 directly. But okay, so greater or equal to 3. So these are Riemannian asymptotically Euclidean manifolds. Possibly they can have horizon boundaries representing black holes. So boundaries say outermost minimal surface, possibly with horizon boundaries. Then scalar curvatures. Scalar curvatures are greater or equal to 0, like in positive mass theorem. And then, okay, positive mass theorem of such manifolds tells you that mass, ADM mass, is non-negative and 0 if and only if the manifold is isometric to the Euclidean space. So the stability will tell you what happens when the mass is almost equal to 0. So, well, let's say so. Then ADM of MIGI, of the metric GI. So if the mass goes to 0, then the sequence MIGI converges to the Euclidean space in the intrinsic flat sense. So I put F here. It converges to R3 in the intrinsic flat sense. So this conjecture, like available proofs. So we have first one from Sarmani-Lee from 2011. That was for spherical symmetry. Then we have Huang, Li, Sarmani for graphs. I think around 2014, maybe a bit wrong with the dates. And then, yes? Oh, okay, yeah, implies. Sorry. Yeah. So masses go to 0, converges in intrinsic flat sense to R3. Yeah, so Huang, Li, Sarmani we have, and then, we have Huang, Li, Piralis. So it's like an extension of this work in 2021. I think Raquel will be talking about this work in this conference. And then there are some other works. I will just mention works of Brian Allen, who assumed some foliations by, say, inverse mean curvature flow, smooth foliation by inverse mean curvature flow, and so on. There is another result which is maybe not quite GR, but it has also connections to GR, and also in this result we have also lower bound on scalar curvature. So this kind of shows that intrinsic flat convergence works well in combination with lower scalar curvature bounds. So we have also stability of Taurus conjecture. So I'm not going to write the precise formulation of this, but there is a classical result, which I guess conjecture itself goes back to Girosh, and not the stability one, but the Taurus conjecture. So there is a result which was proven by Shen and Yao and by Gromov and Lawson, which says that, if you have a metric on a torus with non-negative scalar curvature, then it must be a flat metric. So this is very similar kind of in formulation to rigidity of positive mass theorem. And in the stability or in the conjecture. So I guess conjecture by Girosh was for all n greater or equal to 3. Proved by Shen and Yao is between dimensions between 3 and 8. Greater or equal to 3, less than equal to 7. Gromov Lawson under spinor assumption. And so in stability results, maybe I can just say briefly a couple of. So Right. So all this is like, I mean, stability of Taurus conjecture was, of course, studied also in other senses. I mean, there is a work using Ricci flow by Bamler and Paolo Burhargim. But like in the intrinsic flat sense, so conjecture kind of was brushed up by Cristina Sarmani. So like the version most suited for intrinsic flat convergence was formulated by Cristina. So we have a work by Brian, Allen, and others. So all this like a very recent 2019. So they studied warped products. And then we have a graphical case by Cabrera Pacheco, and Ketterer, Christian Ketterer, who's also here, and Raquel Perales. So then we have some more works by Allen alone for conformally flat metrics, and we have also Chu and Lee, I believe. So this is kind of extension of Allen's work to conformal to metric of bounded geometry, I think. So I hope I have by now convinced you that intrinsic flat convergence is useful and that it makes sense. Yeah. It will take me a little bit to formulate it, but I mean, you need kind of almost non-negative scalar curvature, and then metric will be close to flat metric in intrinsic flat sense. I think there must be some volume lower bound, so it doesn't collapse here. Right. Okay. So how are we going to define intrinsic flat convergence for spacetimes? So maybe actually I'll use some blackboard. So plan how to define. We will define space-time intrinsic flat distance. Yeah, I will call it DSF. And actually, in parentheses, I will kind of write the status of this plan for something which we called cosmological spacetimes. Even though I think our terminology may be a bit different from what is standard for cosmological spacetime. So cosmological. Okay, so first of all, we would like to convert spacetimes to metric spaces. Yeah, so the definition of a cosmological spacetime I give right away after this plan. It's kind of similar to usual definition. Well, okay, so this conversion has been already done, and the null distance was mentioned already today, I think, by Clemens. This is done. This is work of Sarmani Vega from 2011. So basically, for this cosmological spacetimes, there is a natural object which is called the cosmological time function, and then there is an object that one can associate to it, the so-called null distance, and it will be a definite metric for this class of spacetimes. But actually, if you want to define this, so I mean, this of course uses kind of builds upon the intrinsic flat distance of Sarmani and Wenger, and this distance is defined not just for metric spaces. I mean, having just metric spaces is enough for Gromov-Hausdorff distance, but for Sarmani and Wenger's intrinsic flat distance, we also need a structure of an integral current space. So I mean, I'm not going to say in detail what it is, but we need a certain charge structure, so the so-called Lipschitz Lipschitz charts. So we need to kind of cover our metric space by countably many charts such that kind of distance in the chart is Lipschitz function with respect to metric distance and vice versa. So in this we did with Christina for this class of spacetimes. So we did it quite a while ago, but yeah, it's not in a published work yet. So, well, okay, once this is done, so we have objects to which we can apply Sarmani and Wenger's intrinsic flat distance. But natural question to ask here is, can we kind of, from this metric space, recover back our original spacetime? Namely, we would like to recover the causal structure. And this will be important when we try to prove a theorem saying that distance between two spacetimes is zero if and only if they are there is a Lorentzian isometry between them. So well, so question is, can we recover causal structure back? Yeah, kind of back from this metric distance, and yes, we can for this class of spacetime. So this is our work, which has been, yeah, it's on archive already. Okay, once this is done, we can. This doesn't move anymore. Let's try this. Yeah, well, okay. Once this is done, we can now try to define yeah, kind of distance between this kind of metric spaces, kind of building upon intrinsic flat distance. But okay, this object that we define here, it has to be kind of reasonable. So we needed to pass a number of tests. So it needs to pass some tests. Yeah, so of course this result, which I told you, yeah, so intrinsic space-time intrinsic flat distance, let me call it 1, is 0 if and only if space-times are isometric. I mean by this there is a Lorentzian isometry between them. So the isometric is Lorentzian manifolds. Yeah, and then also for intrinsic flat distance and convergence, there is a compactness theorem by Wenger, which says that, well, under very mild assumptions like bounds on volume and diameter, we have yeah, the convergence of a subsequence. So, I mean, here we would like to have a compactness theorem too. Yeah, and preferably also under such mild assumptions without imposing too many additional requirements. Yeah, so this is a plan. I mean, this last part. So this is also our work. Well, it's in progress, but we have quite a bit here to say, and I will say about it later. So yes, let's start by some definitions. So first definition will be that of a cosmological spacetime. Okay, so, well, we start with a spacetime. So far I don't have any dimensional restriction. Later on I will have. So let this be a spacetime. So we will first define the so-called cosmological function. So a cosmological, or maybe the cosmological time function. The cosmological time function. So that's definition of Anderson, Galloway, and Howard. But there is also a definition of Wald and Yip. So, well, this is defined like this. Basically, no, not in the soup. So, yeah, so that's basically how to say how far back on past causal curves we can get until we hit the boundary, kind of at where or Big Bang where everything started. So, okay, so it will be supremum on gamma. So gamma is from 0, 1, say to n. So gamma of p is 1, and gamma is past causal. Okay, and this is just, well, basically Lorentzian distance, Lorentzian length of the curve. So that's minus g gamma dot s ds, integrate from 0 to 1. So just, yeah, this is Lorentzian length of the curve gamma. Right, so we will require that this is the so-called regular cosmological time function, which means that, yeah, basically it converges to 0 on all inextendable past causal curves. So we require gamma, not gamma, tau, tau to be regular. Yeah, so that is, we ask tau to converge to 0 on inextendable past causal curves. Okay, now what we mean by cosmological spacetime. Yeah, so if in addition, yeah, so cosmological spacetime usually assumes some compactness assumptions. So in our case, it's the following. Yeah, so we will require that tau inverse of T1, T2. So like interval between two times, we take its inverse image by tau. So we ask it to be compact. Yeah, for all, well, here T1 less than T2, less than infinity. Well, then, yeah, then we say that Ng is cosmological spacetime. Okay, so I will now define the null distance of Sermani and Vega. I mean, it doesn't have to be defined just for this class of spacetimes, but it's defined much more generally and will be a definite metric for a much larger class of time functions. But yeah, for convenience, we do it for cosmological spacetimes, and maybe let me put it here. So this is null distance. So that's by Sermani and Vega, 2011. Right, so, well, we have 2 points, P and Q, and we will be considering all piecewise causal curves between them. So this is beta, it's piecewise causal. So it can kind of go backwards and forwards to the past and to the future, but each segment is causal. either past causal or future causal. So we first will define the null lengths of this curve beta. So null lengths of this. So L hat tau of beta. Well, this is just, this will be a sum. So let me call this points, breakpoints here somehow, x0, x1, x2, and so on. This q is xk. So yeah, this is basically, we just measure how much time passed has passed between each pair of breaks. So like between here and here, and then between here and here. So we'll get, and then we sum everything up. So we'll get tau xi plus 1 minus tau xi, I from 0 to k. Well, k minus 1. So that's null lengths of this curve. And well, the null distance. Well, we just take, so that's defined d hat tau pq. Well, we will just take the infimum of this, infimum over beta of L hat tau of beta. Right. So for in a cosmological spacetime with regular cosmological time function, this is definite metric, satisfies all the axioms and so on. Maybe some remarks here. Yeah. So one remark is that if okay, Q is in the causal future of P, well, then this is very easy to compute. So this is just, so the hat tau of P and Q, this is just difference in tau for these 2 points. So because, well, because the curve beta achieving this infimum here, it's just a curve of one, which has only one causal segment, future causal. Well, if you add more wiggling, it will just increase its null length. Yeah, so another thing to note here probably is, yeah, if Q is not in the future of P, then it can look like this. Well, yeah, so like imagine 2 points which have space-like separations, then you will need to take many such kind of small segments wiggling back and forth, and the causal curve, which is piecewise future, say, achieving this infimum will not exist, of course. Yeah, so, well, so nice property of null distance has been pointed out in, so let's say so in Minkowski, and the so-called generalized FLRW spacetimes. So these later ones are kind of warped products in the form minus dt squared plus, so warping function is like on a spatial part of the metric. So this H is a fixed metric. So cosmological time function in this case is just C. Minkowski also fits this form for F kind of equals 1. Yeah, so in this space-time, there is a nice property. So, well, kind of this. So we have this, but for this space-times we have both ways. Yeah, so we have d hat tau of P in Q is equal to tau of Q minus tau of P. So this is if and only if Q is in the future of P. So this is very nice because, yeah? Yeah, you have to, yes, exactly, you have to put, yeah, it's not all way, otherwise it's not a regular time function, but yeah, like upper half form. Right, so I mean, this is very nice because here we can kind of recover causal structure just from this relation. I mean, all points satisfying this are in the future of P. Well, something. Okay, I guess I have enough space here for two theorems here and here. Yeah, maybe I should say a word. So this was proven. Well, this is again Sarmani and Vega. This work of 2011, but also this is a work of Allen and Borcher from 2021. So where they studied this class of spacetime, so they converted them to metric spaces using null distance, and then they studied their intrinsic flat convergence. So there is also a kind of continuation of their work in the setting of length spaces by Kunzinger and Steinbauer. Okay, so we have two theorems. So theorem one, so this is by me and Sarmani. So the theorem says that, let's call it star. So the star holds in general and cosmological this holds in general cosmological spacetime, so one can say that null distance in cosmological spacetimes encodes causality. So in this class of spacetime, so we can kind of cosmological spacetimes we can convert them to metric spaces, but then we can canonically convert them back. Right, so we can recover causal structure from time function and the respective null distance. Okay, and then I have one more theorem, which is, we call it an isometry theorem. So this is also, this is on archive in 22. This is also in the same work, let's call it theorem 2. The theorem is the following. So this theorem is very important for for passing this test. So that the distance is 0 if and only if we have Lorentzian isometry. So we have two cosmological spacetimes with respective time functions. So we have two cosmological spacetimes. Okay, and then or actually if. So say now we have, if we have a bijection from N1, 2, and 2 is a bijection such that, okay, we wanted to preserve the time functions. So let's see. So tau 2 composed with f. So let it be 1. This is the same as tau 1. So it preserves the cosmological time function, and 2, it has to preserve the distance. So d hat tau of T1 of P and Q is the same as d hat tau 2 of f of P and f of Q. Okay. Okay, then in this case, f is a Lorentzian isometry. Lorentzian isometry, so it's a diffeomorphism in particular. Okay, I need to put some restrictions here. So this holds, yeah. So dimension here is n+1, so n is greater or equal to 1. For this theorem, we need a bit more restrictive. So here, this holds for dimension n+1 for n greater or equal to 2. So, right. Let's see. So actually, with this theorem at hand, we kind of completed all part of this plan, which was on this board. So now we can start defining space-time intrinsic flat distance between space-times. Let me see. So like let me give you some possible candidates. Okay, so kind of the very first and naive try would be just, okay, we just convert our spacetimes to metric spaces and and take intrinsic flat distance between them. So it will be just intrinsic flat distance. I will just write n1 d hat tau 1. So I do not write the charge structure for saving the time. So yeah, so we just take intrinsic flat distance between this converted metric spaces with the charge structure. But it turns out this kind of definition is not good. So well, the reason why it is not good, because it doesn't keep track of the time. So it doesn't keep track of tau. Actually, in some cases, this can be repaired. So what one could ask for is that, okay, the kind of zero level of tau in this and this space-time should match somehow. But this is not a very natural assumption here, because, well, under intrinsic flat convergence, this kind of levels can just disappear in the limit. But this can still work, like, say, for big bang spacetimes, where you can have kind of natural structure which can be matched. Okay, we can do try to do the following then. Okay, let me see if n1 and n2. Let's do the following. So I will define kind of this things. It's like a stripe between two times, two levels of tau. So tau inverse I of st, this interval. Okay, so actually well, maybe I should say here that this function tau, so in general it's not smooth, but it's Lipschitz. And for almost every S and T, this will be a nice object which we call integral current spacetime. Yeah, this object is such that we can define, intrinsic flat distance of Sarmanin-Wenger is defined. So we just take this. So this is defined for almost all S and T. And then we have to take essential supremum of this, like overall S and T's in some interval. So what about this definition? So actually, we have tried, and this definition kind of passes these two tests. So this theorem is working. So kind of the idea is that, okay, if this is 0, then, okay, this is a supremum. So it means that intrinsic flat distance is 0 for all these pairs, and this is quite strong. So, I mean, we can use this information to patch up this, like one uses some kind of diagonalization argument, and then one can construct this bijection that is required, that kind of is enough for having Lorentzian isometry in this theorem. So here 1 and 2 are okay. Well, but then of course there are more things than what we would want, and what that I haven't put on this list, and this feels a little bit too strong with this essential supremum here. So we have also another version, which is, maybe I'll put it here. So, and I guess after that I will have to stop. Right, so well, that's the same, but yeah, we take again, yeah, same as before. But then we actually, for many arguments, like in this compactness theorem and in this diagonalization argument that we need for this first theorem there, so it's enough with having kind of a countable dense set. So let me put it like this. So we'll take supremum of this for all S and T and some tau. So that's like capital tau has to be, or no, it's capital T, italic T. So, and then we take, yeah, infimum of this overall T's, and this is countably dense. So this is less restrictive, this definition. So this is always less or equal to this one. And unfortunately, I don't have time to tell you. So I somehow wanted to tell you something about the proofs of these two theorems, but I don't have time. But if you would like to know, please ask me afterwards. Thank you very much.